Alright, so let's start the exercises of this section. So this first one is this. It has been conjectured that there are infinitely many prime numbers of the form n square minus 2, where n is some positive integer, of course. We have to exhibit 5 such primes. So it's only a conjecture. Okay, so likely no one has settled this yet. So we just have to find 5 such examples. Two square minus 2 is of course 2, which is a prime. Then 3 square minus 2 is 9 minus 2 is 7, so that is again a prime. 5 square minus 2 is 25 minus 2, that means 23. That is also a prime. So these are known, we already know these numbers to be primes. Then 7 square minus 2 is 47, that is another prime. And how many have we written? 1, 2, 3, 4 and another one. And 9 square minus 2 is 79, which is also a prime. So you can take these as 5 examples of n square minus 2 which are all primes. Number 2, now another conjecture which is false. Give an example to show that the following conjecture is not true. And the conjecture is this: every positive integer can be written in this form. In the form p plus a square, where p is either a prime or 1 and a is a non-negative integer. So that's the conjecture. The conjecture asserts that every positive integer is expressible in this form, where p is not necessarily a prime, it's either a prime or 1 and a is a non-negative integer. And the counter example you can take is 25. Note that 25, okay, so if we try to write 25 in this form, then what do we get? Now in this form means what? In place of that p, it will either be a prime or 1. So let's see what happens if we take 1. So 25 is of course 1 plus 24, but then 24 is not a perfect square, where 24 is not the square of any integer, and hence also not the square of any non-negative integer. Also, okay, so that is not possible. So we cannot write 25 as 1 plus something square. What about the other possibilities? Maybe if we start considering squares, maybe we will get a prime. Let's see. Also, so we start considering squares means let's try to write 25 as 0 square plus 25, then 1 square plus something like that. Let's see what happens. Obviously, if our square is 0 square, then the other thing is 25. Then we can continue writing like this, okay, some equalities. 24 plus 1 square, then if we take 2 square, we will get 21 plus 2 square. If we take 3 square means 9. 25 minus 9 is 16. If we take 4 square, then that means 16. So on this side we will have 9. 9 plus 4 square, and that's it. Can we write any more? No, we cannot write, because if you take 5 square next, then the remaining, the other summand is 0. Let's just write that also. Where none of the representations is of the form p plus a square. Okay, where we understand now what p is. So that's why 25 provides us with a counter example to this conjecture, and that's it. We were asked to find one such example and we have found it. Next. 3. Prove each of the assertions below. Okay, there are 5 assertions. A. Any prime of the form 3n plus 1 is okay. Any prime of the form three n plus 1 is also of the form six m plus 1, because there are 5 parts. So instead of writing them down, all of them now itself, let's just solve this one and then go like that. So we are being asked to show that any prime number of the form 3n plus 1 must also have the form 6m plus 1. That is, if you divide a prime number by 3 and have remainder 1, then on dividing that same prime by 6, you must have remainder 1 again. Let P be a prime of the form 3n plus 1, where n is a positive integer. Positive because 1 is not a prime, so n cannot be 0. Since, so what is the smallest prime? The smallest prime is 2, but 2 is not of the form 3n plus 1, because if we divide 2 by 3, then the remainder is 2, not 1. Since 2 is not equal to 3n plus 1, we have p greater than 2. So p is not equal to 2. P is a prime, but it's not 2. But 2 is the only even prime, so that means p has to be odd. So p is odd. P is odd, but if P is odd, then P minus 1 has to be even, that is P minus 1 is 3n is even. But the evenness of 3n then has to come from n, because 3 is relatively prime to 2. We should of course write it properly. Since the GCD of 3 and 2 is 1, Euclid's lemma implies that n has to be even, because 3 does not contribute anything to the evenness of 3n. So this implies that n has to be equal to 2m for some positive integer m. Okay, why should we have m positive? Because n itself is positive, that's why. But then p equal to 3n plus 1, but because n is 2m, so this is 6m plus 1. Okay, so that's how we have our result. Next, part B. Each integer of the form, this one is much easier. Of the form 3n plus 2 has a prime factor of that form. Yeah. Okay. Solution. Now we know from the Euclidean algorithm that any integer is of the form 3n or 3n plus 1 or 3n plus 2. That's because when we divide an integer by 3, These are the only three possible remainders, 0 or 1 or 2, and accordingly those three forms are only all the possibilities. Okay, now note carefully that any integer of the form 3n plus 2 does not include the numbers 0, 1 and -1. Okay, because if your integer, well, in this problem I don't think, okay, it's written as an integer. Let me just see one thing. Okay, -1, can -1 be of the form 3n plus 2? Is it possible? Yeah, of course it's possible. Oh, if this is the case, because you can take n equal to -1, no? Okay, so what is being claimed here is actually not true for this -1. You can do one thing, you can include positive integer here. You can include this adjective positive if you want, because anyway we are considering, although we can consider integers, but then we have this problem and the claim is strictly speaking not true because of that thing. You can see that -1 is also an integer of this form 3n plus 2. But the problem is that it is being asserted that any such integer has a prime factor of that form, but -1 does not have any prime factor at all, let alone of that form, okay, of the form 3n plus 1. So the assertion in fact fails if we do not additionally assume something else to rule out this possibility, -1. So how should I modify this? I mean, one way of modifying it is to only consider positive integers. Another one is to just simply rule out -1 by explicitly saying so, which will sound very odd. Instead, let me just do it for positive integers. Okay. Since 1 is not of the form three n plus 2, any integer n, oh, we cannot take n, let's call this m, say. Any integer m of the form 3n plus 2, any integer, any positive integer I should have mentioned. Let me write like this: any integer m greater than 0 of the form 3n plus 2 must be greater than 1. And because of this, now we can apply the fundamental theorem of arithmetic to such an integer, and by that theorem m will have a prime factorization. Okay, m will be a product of some unique primes determined by m itself. Then by the fundamental theorem of arithmetic, which is theorem 3-2, if I am remembering correctly, m is the product of some primes in such a product, each prime is of the form three k. You understand that k is an integer, right? Is of the form 3k or 3k plus 1 or 3k plus 2, because these are on all the forms that an integer can be in. Okay, there are no other forms. Now, if all the primes in the product are of the form 3k or 3k plus 1. Probably I should not have said it like this, but more precisely I should have written this. Now if each prime in the that way it will sound better. Now if each prime in the product, in this product, is of the form 3k or 3k plus 1, then M is also of the form 3k or 3k plus 1, but that cannot be because it's given that M is of the form 3n plus 2, but that is not possible. And that's why at least one of the primes must be of the form 3n plus 2. So at least one of the primes in the product must have the form 3n plus 2, but there is one more maybe a source of doubt. How is this true? How is it that if each prime of the product is of this form 3k or 3k plus 1, then the number itself is also of that form? Let's see. What happens if we take a product of two numbers of the form 3k? Let's see that. Say 3k1 and 3k2. Then the product itself is again of that form, because you can write it as 3 times 3k1 k2, where 3k1 k2 itself is some integer. What happens if we consider the product of a 3k1 with another number of the form 3k2 plus 1? In that case, you have again 3 times k1 times 3k2 plus 1. So again of that form, 3 times some integer. But what if we consider the product of two numbers of this form, 3 times something plus 1? then it will be again a number of this form itself, and you can see that this will be what yeah, let me just first carry out the multiplication. 9k1 k2 plus 3k1 plus 3k2 plus 1. So this is 3 times 3k1 k2 plus k1 plus k2 plus 1, 3 times some integer plus 1. So we see that if the prime factors are of one of these forms, okay, not all of them simultaneously, but you understand each one of them is of this form or this form, then we are trapped in those two forms only. So if this is the case with two numbers, then any number of factors will also be of one of these forms, and that will not make m of the form 3n plus 2, but it's given that m is of the form 3n plus 2. So at least one of the factors must be not of any of these two forms, that is, it must be of the form 3n plus 2, and that's how we have our conclusion. Next, C. I need ink. In C we have this. The only prime of the form n cube minus 1 is 7. There is a hint also, but it's very easy. I mean, it is something we already know, that is the factorization of n cube minus 1 from elementary algebra. The thing is this: if n cube minus 1 is a prime, but let's write the factorization also, that is n minus 1 times n square plus n plus 1, this we already know this formula, is a prime, then by the definition of primality of an integer, because this is already a factorization of n cube minus 1, one of these two factors has to be 1 and the other one has to be a prime. This is a prime, then either n minus 1 is a prime and n square plus n plus 1 is equal to 1, or n minus 1 should be equal to 1 and n square plus n plus 1 is a prime. So there are two possibilities, but let's see what we get from the first possibility. Now, if n square plus n plus 1 is equal to y, is it mentioned that n is positive? Oh, n has to be positive, right? Because we have cube. If n is negative, then n cube minus 1 is a negative integer. How can it be 7? There may be a terrible mistake while solving this, right? See, what is it that we have been asked to show? The only prime of the form n cube minus 1 is 7. If you start by assuming that n cube minus 1 is 7, then actually you are not doing anything. Okay, you have to assume that this is a prime and then prove that it has to be equal to 7. Okay, so that's what we are doing. Now, if we assume that this is the case, if n square plus n plus 1 is equal to 1, then the only possibility is this, n equal to 0. But then n minus 1 would be equal to minus 1, and that is not a prime. So we must have, so that means the other possibility should be true. N minus 1 equal to 1 and n square plus n plus 1 a prime. That is, we should have this. And in this case, n from this equation we get n equal to 2. And so what is n square plus n plus 1? 4 plus 2 plus 1, 7. See? So that's how we have settled this. Next, D. Two more are there. The only prime, again another such, but now it's not a prime of some form, but slightly something else. The only prime P for which 3p plus 1 is a perfect square is p equal to 5. Solution. Obviously, 3 times 5 plus 1 is 16, which is a perfect square. Now we have to show the converse, that is, if this is a perfect square, then p must be equal to 5. Now let p be a prime such that 3p plus 1 is equal to k square, where k is a, let's take in general a non-negative integer. You can take positive also. Okay, but the value of k is not that much important, but let's see the first few values of p. Note that three times 2 plus 1 is equal to 7, and 3 times 3 plus 1 is equal to 10 are not perfect squares. Okay. Okay. But do I really need to go through these cases? Now there is no real need to look at these two cases. Yeah, let's just work with this equation itself. Now look at this. So from this equation, what is 3p? 3p is k square minus 1, which can itself be factorized as k plus 1 times k minus 1. And let's just restrict this a little more, because there is no point in taking k equal to 0. Since p is a positive integer, so 3p plus 1 can never be equal to 0. So k is a positive integer. And now we have this. Now in the next line I write this by theorem 3.2. That means by the fundamental theorem of arithmetic. Either 3 is equal to k plus 1 and p is equal to k minus 1, or the other possibility, namely 3 equal to k minus 1 and p equal to k plus 1. We will explain why. Or 3 equal to k minus 1 and p equal to k plus 1. So what is it that we have done here? We see two numbers, right? One on the left side and one on the right side. Each one of them is a product of two integers. However, the product on the left side is actually a prime factorization of what? Of the number that we see on the right side. Why is that so? That's because 3 is a prime and p is also a prime. And from the uniqueness of such prime factorizations, we know that when we factorize this number, whatever number it is, the number is k square minus 1. Whenever we factorize this, it has to be 3p itself. It cannot be anything else. No other prime can arise in this factorization. That comes from the uniqueness of such factorizations. Okay. So you can, but at the same time you see another factorization. This may or may not be a prime factorization, that's not the point, but you see another factorization. Now, if it happens that this factorization actually is not a prime factorization, maybe, who knows, maybe one of these two factors is actually not a prime, it's a composite integer. Okay, that may be the case. Or one of these two things may be actually equal to 1. That is also a possibility. But you will see that if you argue with these things, you ultimately get to the conclusion that one of these two things has to be true. For example, say you consider k minus 1 to be equal to 1, say. Okay. So in that case, what happens is that k minus 1 is 1, but k plus 1 is 3p. That possibility is also there. So what happens if k minus 1 is 1? Then k is equal to 2, but then what is k plus 1? Then k plus 1 is 3, but at the same time k plus 1 has to be this entire thing, because the other thing has been taken to be minus 1. 1. So you get 3p equal to 3. But from that, you get the conclusion that p is equal to 1, which is a contradiction because p is a prime. It cannot be 1. So that thing is ruled out. Similarly, the other possibilities can also be ruled out, and you will ultimately come to the conclusion that either this is true or that is true. I am not going into the details of exactly how many cases you have to, you will have to see 2 or 3 more cases like this. And one of those cases, keep in mind, maybe this also, that k plus 1 is, at least one of these two is composite. That is also a possibility. But then do not forget that since 3p is equal to this, so 3 has to divide this product. At the same time, p also has to divide this product, and being primes, they will divide at least one of these two things, both of them. That is, either 3 divides k plus 1 or k minus 1, also p divides k plus 1 or k minus 1. So going through all those things, taking everything into consideration, you will see that either this is true or that is true. Okay, so this part I am just skipping some steps. Now let's look at the possibilities for once. What does this give us? This gives us the possibility that k has to be equal to 2. But if k is 2, then p has to be 1, which is not possible, right? If, so that's where we start to rule it out. If 3 is equal to k plus 1, then k is equal to 2. But then p is equal to k minus 1 is equal to 1. A contradiction. So that means we cannot have this. Thus, we must have 3 equal to k minus 1, i.e. k has to be equal to 4, and hence p equal to 4 plus 1 equal to 5. Yeah, now it's okay because 5 is a prime. So you see that 3 times 5 plus 1 is a perfect square, but if you assume that it's a perfect square, then p must be equal to 5. So that's why that is the only prime for which this happens. And lastly, part E. The only prime of the form n square minus 4 is 5. And I will not solve this fully, I will just give you the hint. By now you can, of course, I hope you can see how to go for solving this type of problems. In these problems, either the number that is given to you is given in a form that is readily, immediately factorizable using algebra, because these are algebraic expressions, or they will arise in a situation where some other algebraic expression you will come across, like that one, which is factorizable, like k square minus 1. Okay, then you can argue using divisibility and primeness. So here the solution goes like this. You are assuming that n square minus 4 is a prime, but already it has a factorization in the form n plus 2 times n minus 2. Now if this has to be a prime, there are two possibilities. Either n plus 2 is equal to 1 and n minus 2 is a prime, or n plus 2 is a prime and n minus 2 is equal to 1. You can actually immediately see that this possibility does not give you sensible conclusion, because if n plus 2 has to be 1, then n has to be minus 1. Well, in that case we do get n minus 2 equal to minus 3, which technically speaking is a prime, but by prime we mean positive primes. Okay, so this possibility has to be ruled out. So that means we must have this, but then n is 3 and so n plus 2 is 5. Okay, so that's how you can write the solution more formally, and that's just it with this entire problem. And that's also all for tonight. Our next upload is this coming Friday, and on Friday let's do graph theory once more. So see you on Friday. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.